Welcome back, aspiring smart contract architects. You are tuning into another Forge College Explainer. And wow, if you are following our Solidity from Zero track, huge congratulations are in order because you've officially made it to the capstone project. Today, we are covering the project overview and requirements. Before a single brick is laid or a single line of code is ever compiled, we need a solid master plan, and that is exactly what we're drawing up right now. Now look, we all know that universal developer urge, right? You literally just finished the previous lesson on extending modular contracts, your fingers are practically vibrating over the keyboard, and you just want to skip the documentation and jump straight into the matrix. But hold on, let me stop you right there. Building a complex Web3 architecture without a deterministic plan isn't just risky, it is a guaranteed recipe for $1 million spaghetti code disaster. So, to prevent that kind of chaos, we are going to draw up the blueprint for your capstone today. Here's a quick look at our agenda. 1. The mental model. 2. Scoping responsibilities. 3. Interfaces and criteria. And 4. The blueprint workflow. Let's get right into it. Kicking things off with Section 1, the microservice mental model. We are adopting a microservices approach for our smart contracts. We really need to borrow a page from traditional back-end engineering here. Instead of building this tangled, massive monolith where every function is constantly tripping over the others, I want you to imagine your architecture as a series of totally independent, isolated rooms. These are your microservices. Each module owns a single, strictly documented responsibility. It's an approach that makes our code infinitely easier to audit, upgrade, and ultimately secure. So if these modules are independent rooms, how do they actually talk to each other? Well, through interfaces. Think of them as the literal doorways between your rooms. And these aren't just empty open frames, okay? They are highly sophisticated security checkpoints. An interface boundary is defined by exact function signatures, event shapes, and very specific error semantics. If the incoming data doesn't perfectly match the doorway's exact shape, boom, the transaction immediately reverts. Now, building on what you learned in the last lesson, you might be wondering what happens when you need to connect a brand new room to an older legacy doorway. You obviously can't just take a sledgehammer to the wall to make it fit. That is exactly where adapters come in. Think of adapters as hallway translators. They sit right between those older legacy interfaces and your super compact modern ones, basically ensuring everything connects perfectly without compromising your beautiful new architecture. Moving right along to Section 2, Scoping Responsibilities. It's time to get really strict about what our code does. You wouldn't buy a toaster that also tries to manage your crypto portfolio, right? I mean, it would probably burn your bread and short your Bitcoin at the same time. You need to avoid compound responsibilities like the plague. No single module should be trying to manage balances, enforce access, and handle governance all at once. What we want is ruthless, decomposed responsibility. For example, a token accounting module has one job: maintain balances. If it needs to verify permissions, it doesn't do it itself. It just asks the access control doorway. Decompose absolutely everything. All right, Section 3, Interfaces and Acceptance Criteria. This is where we focus on passing our building inspections. So here is the big question. How do we prove the plumbing actually works before anyone moves in? Or, in Web3 terms, how do we absolutely guarantee this smart contract is bulletproof before real user funds start flowing through it? We do it by converting all of our high-level architectural decisions into hard automated tests. Each one of those interface doorways we talked about essentially becomes a rigid test boundary. To pass inspection, you need a serious, multi-layered approach. First up, unit tests. Basically, does the room work perfectly when the door is closed? Next, integration tests. Do those hallway translators actually do their jobs? Then we throw in property tests to check invariance across completely random, chaotic inputs. And finally, gas limits. We absolutely must assert strict gas budgets. If a simple transfer costs way too much gas as the system scales up, it outright fails the inspection. Which brings us to Section 4, the blueprint workflow. Let's take all of this from a great idea to a concrete plan. We have a highly actionable 6-step workflow here that maps out your entire planning phase. First, you inventory your existing patterns. Second, you purposefully select up to 4 modules. Keep that scope nice and tight. Third, you explicitly define those interface doorways. Fourth, map out all those tests and criteria we just discussed. Fifth, firmly document your upgrade policies. And sixth, you finally produce the written brief. This workflow takes you from a pile of raw building materials directly to a clean, deterministic document. And your final capstone project brief, it's going to look exactly like this engineering spec table. Notice how beautifully and concisely it maps everything we've talked about. Your specific chosen modules are on the left. You've got their precise interface doorways, their single core responsibilities, again, no toaster portfolio managers allowed, and their specific test expectations. This isn't just a sketch, it's a precise, binding contract for your upcoming development phase. The real beauty of doing all this prep work is that a thorough blueprint makes your implementation completely deterministic. It removes literally all the guesswork. If a sneaky bug appears or a brand new feature is requested later down the line, this document tells you exactly which module to modify, which specific doorway is affected, and exactly which tests you need to write. It turns the art of architecture into a pure, predictable science. So, as you wrap up your project brief, I want you to ask yourself, are your blueprints truly ready for the real world? Could your design withstand millions in total value locked, completely unpredictable inputs, and strict gas constraints without cracking under pressure? Take the time to get this foundation right. It pays off big time. Be sure to visit forge.college to explore our other deep dives and learn more about mastering Web3. Thank you for joining this Forge College Explainer. It's time to stop guessing and start engineering. We'll see you in the next build phase.